Okay, so I think it was already mentioned a little bit, the word revolution here, and what I'm going to try to explain to you is how far the mindset, the understanding we had, or where we're sitting in the universe, why we have the solar system, and why there is life on Earth, has dramatically changed. It has changed in such a way that there is no a new momentum, there are really a new development going on that was really impossible 30 years ago. So we have plenty of planets, so I think everybody is aware of it. Just open the press, there is every week a new announcement, there's a new planet detected, so there's really tons of planets being found. But practically it's interesting to go back on what exactly we are detecting. Well, first, most of this planet that we know, we can say that star has a planet, that one has a planet, or 2 or 3. We don't see them. It's quite extraordinary when you think about this, is we have so many discoveries without seeing anything, and it shows a lot about how science works. And you clearly know that you can study the beginning of the universe into big accelerator on the sun, for example. You don't really see it, you have equipment and stuff. So we're using equipment to do that. And what happens is when you have a planet orbiting a star, you have that kind of situation happening. So it's moving a little bit the position of the star, and if you have the right equipment, you can detect this motion. Now, the way we did that 30 years ago was by simply measuring the change of the speed. So we didn't really measure the positioning of the star, but really the change of the positions, derivative. Tomorrow, there will be definitely planet detected by seeing the motion change into the star with a satellite called Gaia, which is producing a lot of results. But up to now, we're only using this technology, which is quite often called radial velocity, and we use the Doppler effect, the light from the stars and Doppler effect to detect this. And some of this system, if you are lucky, you may be just in the right angle and looking at the star and the planet at the time they are crossing each other. So if you have the right angle, you just have a moment when the planet orbit is going to cross your line of sight, and that creates what's called a transit, similar to a solar eclipse that we have here. So this is essentially the two main technology being used to do that. Now, what is fascinating about that is if you go back 30 years ago, nobody would have bet on these technologies, for a simple reason that this technology were not mature enough to reach the level that you needed to detect this planet. Because the planet is tiny. Because it's tiny and the ratio of mass between the star and the planet is huge, anything that the planet does is tiny. It requires a lot of equipment. So that was really the first element. And I would like to spend a bit of time on the equipment level. That's not the only reason, but that's one of them. So speaking about equipment that was mentioned just before, we developed a machine with Michel at the Observatoire de Haute-Provence in south of France. That was not bad the way he did it. Huh? That is the one. It's not working anymore. No, it's an exhibit. So if you go there, I would recommend. It's a beautiful area of south of France. You can see the machine. And the reason why I show that is I think we have to remind ourselves that science is collecting data. It's about data. That machine was collecting data. But what makes progress in science is to collect a kind of data that no one has done before. And that's exactly what that machine was doing. And this machine was really, let's say, unique in its style because we implemented a lot of small elements together that were completely new at that moment. The first one is this big piece of optic you see here that's called a high-resolution grating. That was the first of that kind built used for spectrograph. That was this first machine that did it. Now there are plenty of them. They called R4 gratings. The second reason why we're using is this tiny orange tube you have over there here. That's optical fibers. At that moment, they started to be used for telecommunication purposes, but most of them were operating in slightly infrared because that works much better. There's much better transmissions. Very few would be available for astronomers. But they started to pop up, And the difficulty was, how do you implement these optical fibers into an astronomical equipment? Because what you really have to deal with is to make sure the maximum of the light that reaches your telescope should reach your machine. You don't want to lose any of this light. And we did it right, and we were amongst the very first one to implement that. That was a major change, because when you have a tube that brings the light from the telescope down to somewhere else, you don't have your machinery hanging behind the telescope. And then you don't suffer the change of gravity, you don't suffer the change of temperature. So you have a concept that was stabilized instrument. So the instrument was stabilized in a sense that it didn't have too much change that would have completely made impossible the measurements of a very tiny signal that we needed to detect for the planet. And the third equipment, is good to also mention that, was a complete new technology in computing power. We're talking about AI right now, and certainly there is a lot of AI stuff that will pop up in science because of new technology, but in my days, that was a new machine. The Microsoft technology came up with a simple device that used to be used for mainframe computers. They used to be used by the Cray supercomputer, and some people into Cray left the company, decided to use the chip they had and to implement that into a small computer that was called a mini computer at that time. The only other we had was the kind of MS-DOS system that was not powerful enough. That has been a massive change, not only for us, in many labs in the world, because this machine would give you a lot of power in terms of computing power. Because going from this machinery and the kind of data you produce into the essence of what you want, which is essentially one data measurements, that is the speed of the star, it's quite an extensive series of line of codes, and it took me almost 2 years to build up that program. So to give you an idea how complex that was. These are the three elements that we did right. And quite often people ask us, how come did you make the discovery and not the others? Well, one reason is, I think we did the things right, and we were a bit faster than the other, and we were looking at the data, essentially. So nothing really extravagant, but that's really the story of this machine, which is called LOD. And then the end product for us was we had this magic number, which is 10 meters per second. That was what you expect to have when you have a Jupiter, like our own Jupiter, orbiting the sun. Now come the other bits that is interesting. I mentioned before that the transit technology and the radial velocity technology were not the kind of technique that anyone would use to imagine looking for planets. There has been even paper written in the 90s telling we should not do that. We should not spend the money for that. And indeed, not much money was spent, because that was done on the shoestrings in terms of support, because that was not understood that this would work. And that's very interesting to understand, because that has dramatically changed right now. And the reason why is because we had a pretty good idea that a planet with a mass of Jupiter, which is the biggest planet, has to be somewhere in the kind of orbit that is the orbit of Jupiter. Remind you, Jupiter is 5 times away from the orbit of the Earth. It takes 11 years to go around the Sun. So that is the kind of planet you think about it. All the giant planets are outside, in the outside part of the solar system. That is why when we started the program, nobody, including me and Michel Mayor, were expecting to find anything. And it came up at a complete surprise that we found a planet that had a period of 4 days. So why so? And it's interesting to go back here, because it has profound implications on the understanding of the formation of the planet. To do that, I will show you 2 pictures. One is from space, from the Hubble Space Telescope. The other one is from the ground, from a series of radio telescopes. This is a famous star in the southern hemisphere, which is called Beta Pictoris, very bright. And the scale of these 2 pictures are exactly the same. I just managed to put them on the same scale. So on the top, what you see, you don't see the star, it's masked. There is a kind of a blob black. What you see is a kind of a thin line, which is the reflected light from the star into any small particle that you have in the structure. It's similar to what we call a zodilite in the solar system. The only difference here is there are way more, because that stars are about 30 million years. So it's very early young stars compared to our own system. Just to remind you, we have 4.5 billion years old right now. So it's a very young system, and we see all these bits. So what is striking? Well, there's a lot of stuff here, and you can see maybe another kind of substructure. You would be right, because there is two kind of disks there, and there's a planet there. So I don't want to discuss all this, but just look at this very thin line. I think it's quite fascinating. You end up in the natural structure with something so thin. And that's one of the beauty of physics, because that is exactly what you expect when you have a rotating frame with a potential which is completely symmetric, which is a star here. It produced naturally this effect. So what is great with that is all these tiny grain of solids. You can imagine like the grain of sand if you want to have a picture, a mental picture. They can have much more bigger objects as well. You can also have the asteroids, all the stuff there, but we can think of a lot of small stuff. Well, they're all very close to each other. They're all in kind of a mid-plane, and of course they eat each other, they touch each other, they glue to each other, and that's the reason why we're building planet. We call that the core accretion mechanism, and this is really the way that you kind of build up the planet on the top of each other. No, that's what we have in mind when we make a planetary system. We have this mechanism of the small tiny bits that glue together and form a seed, what's called the core, that is going to attract all the rest of the material around. Now, on the bottom, you have actually a different picture, because we're using then the millimetric wavelength, which is sensitive in that case to a gas, which is CO, the carbon monoxide. So that's what you hear. So the size is very different, what you see, but it's exactly the same scale. So obviously, you don't have this very thin layer like before. Well, if you have a bit of background in physics, you understand this is hydrostatic equilibrium. This is why you can go up to the mountain and still breathe. Otherwise, anything will fall down, but the gas is sustained by the pressure, so you maintain this kind of vertical balance here, and you are quite extended. But there is something else on this picture. There's a kind of a cut on the edge, and that's not a cut by the technology. Technology is amazing here. They could detect anything very small in terms of signal here. It's real. There is a cut. The gas is very extensive in the vertical side, but it doesn't go further. And the reason why it doesn't go further, because the temperature in the disk goes down when you go away from the star. Makes sense. You get closer to the star, it's hotter, you go farther away, it gets cooler. So it becomes so cool, then the gas change state. There is a phase transition and the gas becoming a solid. So in a way, you can imagine this is snowing CO over there. You can do exactly the same for the water. You can do for any gas you have, and the amount of gas is much larger than the amount of solid particle like the silicate you have in the system. So with this picture, you understand that there are tons of particles here that has fall down, which is not into the gaseous form. And this is the reason why we believe that the seed to make a big planet will be faster, bigger, because there's much more material, because they are kind of a flaky, you just build the big stuff very quick, and because the gas disappears after a couple of million years, which is not the case for the solids, it takes much more time, you very quickly build up the giant planet. This is why everybody, including us, were convinced that giant planet has to be outside. So you can imagine the shock when we announced it, and let's be clear, nobody believed it for about 4 years, until a transit was detected. Because it was so much of a change into theory, and not only for the fact we had an object, because people said, well, but if a planet can just not be there, it means what happened in the solar system? And people started to invent mechanisms to deviate from that theory and say, maybe you form a planet somewhere and you move it around, and then the question is, how do you stop the planet, and why the solar system didn't do the same experience the same way? So it became very confusing, and actually, as of today, we still don't know exactly. We have a couple of ideas. We know that the planet can move around, and we know actually that a lot of them did move around. And that was really the kind of a first mental shift that we had to swallow in the story of Exoplanet. After 30 years of discoveries, things didn't improve on that matter, because right now we have a very complex picture, which is all the planet that is being known. Each of them is a dot on a very simple diagram. When you express the period of the orbit, the mass of the planet, that you get some sort from the radio velocity technology, and then the size of the planet, the radius, when you get from the transit. So this is the result of the two techniques that very few people would have bet on 30 years ago to detect planet. It's a completely change of the mindset. And what you see here, and it's quite shocking, that a lot of the planet that you have on this diagram, which I'll point, remember, would fit within the orbit of Mercury. The 90-day would sit about here, so Mercury will be there. So all this will be into the orbit of Mercury. The same here for the mass of the planet. So you have most of the objects that we found that just have no real counterpart into the solar system. And that's a kind of a very disturbing element that you have to get. Now, of course, what is fascinating is it is seen also as a kind of gift of the universe, because it turns out that a short-period planet is very easy to detect with this kind of primitive technology I was describing before, especially the transit, because you increase your chance of having the configuration that creates a transit if you have a short period. You produce a much, and for the radial velocity, the signal is much stronger, because radial velocity is measuring some sort of the shaking effect of the planet. So you get closer, you shake more the stars. So you have a lot of discoveries when you have a short period planet. Now, what is interesting here is to see how completely alone and isolated is the planet of the solar system. I didn't put all of them, I just put some of them for you to figure it out. And because here, a twist that you also have to understand is when you approach a problem in a kind of a global way, the technology doesn't allow you to detect all the planet you want, because the sensitivity will decrease if the planet goes further away, or the probability of a transit will decrease also if the planet goes away. And actually, you have to consider some kind of limitation. So it's kind of ballpark limitations that tell you anything on the right side of that two line, there is no way we can detect it. Of course, there is a gradual decrease. So the closest you approach the border, the more difficult it is. So that's why you have the blob of discovery farther away and you disappear gradually. So it's a very biased perspective we have on the world, because there is a lot of terra incognita. And if you want to compare that, remember the old mapping of the Earth. You see a lot of this map and they don't know how to continue, or they say terra incognita. It's a bit exactly what happens here. So we know for sure what's happened there. The more away you go, the less you know what's going on. But what is extraordinary with this diagram is you can do statistics. It's not easy, and I will not say we completely agree to each other, but there is a kind of a good consensus of the ballpark number of the occurrence of any of this group of planet. They are kind of group. You have this hot Jupiter, similarly to the first discovery, short period, high mass or Jupiter mass. You have this kind of blob of many planets within the orbit of Mercury that are, in terms of size and mass, ranging from Earth-ish to Neptune, and in between you can invent anything you like, super Earth, mini Neptune. So this is exactly what we have here on the other side. And then we have this kind of planet that kind of look like Jupiter, while some of them, it's a log scale, are really much bigger, and some of them are really closer in terms of orbit, like 1 year, so they don't exactly look exactly the same as Jupiter. And some of the orbit, or most of these orbits, are not also are kind of eccentric. So we have now an idea of the likelihood that you would have any of this group of planet on a given star. And the number are kind of a bit shocking for most of the community, because the hot Jupiter is few percent, and that's one of the reasons why we have been successful, because we were amongst the very first one with our American colleagues to observe more than 100 stars. We had 142 stars. The previous team that started a survey of planet and stars has less than 10 stars like the Earth, so that's why they never found a planet like that. So we had 2 actually in the sample, so it matched the number. We have a 10 to 20% of big planets, but they're not exactly like Jupiter. But what is absolutely fascinating is there is more than half of the star. Think about this when you look at the stars. Up to 80%, and again, there's a room for maneuvering here, that would qualify as having a planetary system like that. most of these planets, they don't come alone. There's a couple of them as well. You can have one at short period, another one after late. So there's groups of planets. So the numbers are quite amazing because if you reverse a number, it tells you that the solar system configurations doesn't fit into this number. So they must be less than 20% already by looking at this number, just by looking at this number. So it doesn't prevent any of these planets on short period to have further planet that looks like the Earth. You can imagine a very extensive system of 10 planets like the Earth on a system and no giant planet at all. But in that case, it already tells you the story that we are a bit aside. This is the reason why we consider that we are living a revolution, because we have reset where the solar system fit into the global scheme of the planet in the galaxy. And similarly to the moment when we put the Earth at its right place, which is orbiting a sun, we have set the solar system amongst many systems, maybe not that common, into the diversity of planets you have in the solar system. So this is what is happening. This is what happened really in the last 30 years. And what is amazing with this diagram is when you start looking at the data and you start combining the data, you realize that you can learn way more. Combining the mass and the size of a planet, because some of them, they are in transit, and you can detect the shift in the change of velocity of the star as well, you can build up density diagram. And from the density diagram, you start moving into another dimension, which quite often refer to exoplanetology. You start telling a story about what these planets are made. Depending on the combination of the density you have, there are something you can make and something you can't make. I'll give you an example. These are a kind of consensus, census of all the density we have computed on all these planets we have detected as part of the community effort in the last essentially 20 years here in this case. And what you do see to help you, there's a couple of planets like the solar system, and I just overlay some of this expected theoretical structure you would expect, accounting for all the understanding we have on some of them. I picked the easy one, Jupiter. So we have a pretty good idea how Jupiter is. Essentially, it's just hydrogen, to make it simple, with a tiny core. So you can compute the hydrogen on very high pressure. This is something that our dear colleague studying atom bomb, they do usually, and you can reuse all this phase computation to compute a planet, and you can predict where the planet will be if you change the mass and the size. It's interesting to realize that when you change the mass, it doesn't change very much the size of the planet. It's related to something that you may have heard, which is called quantum mechanics, which divert from the usual behavior of normal gas in this case. But what is interesting, when you come to the end of the diagram, when you come here, you see that this point, the theory density, the density of Jupiter and Saturn that fit about the same to the first order, doesn't reproduce the density of Neptune. And there is a very good reason for that, because Neptune has almost no hydrogen compared to Jupiter and Saturn. So it's a very different planet, and it's quite often considered as a kind of a potential historical seed of how you would start to make a giant planet. If then you have enough material around, you can trap to attract all the gas. So you can imagine Neptune being a failed giant planet. Why fail? It was farther away, had much less material. The dynamic is different when you fall away from the disk. So it's pretty interesting. So it's denser, because hydrogen is the lightest way you can get. So it's much denser, it's down. And then you see this kind of blue line, which is not a real planet that exists, it's something which only exists in computers. If you use water, and you make a planet with water, you ask me why water? Well, very simple reason why water is because we know very well water on high pressure. And thanks to our geophysicist colleagues that needs to understand water to understand the way the Earth works, because the Earth without water doesn't just work. Because the water is the oil for the Earth, and it makes the plate tectonics working. So we have a very good understanding of water, and you can produce what you get. And what you do as well is you produce a planet like the Earth, which is known as a rocky planet in a simple form, and that's the green line. And what you do see is there is an explosion of planet sitting between Neptunes and between rocky planet. And frankly, if you ask me what they are, I just don't know, because they are a mixing of many things. You can, depending on your assumption, play the way you like. You can make a big Earth with hydrogen. You can add mixing Earth with Neptunes, you can have mini Neptunes and remove some element and change it. You can do whatever you want, and some people are studying in great detail right now the detailed structure you have here, because there is really substructure. I don't want to do that, I don't have the time to do that, that give you maybe a clue how come this planet has been formed. So all these planets you have here essentially are fitting inside the orbit of Mercury. So they are unique planets that we cannot study in the solar system. And I'll give you the second hint here of my talk is actually what you have when you study planetary system using the mini exoplanet. You have this immense choice. You have the diversity, but you can't touch. So in the solar system, you can explore, you can bring stuff. In this case, we just can't go, but there are so many, so you get this immense diversity, and that's just really a superpower, and that's what we're trying to build up and to understand. Of course, it's also a complication, because the diversity doesn't fit in the simple diagram that we have in our solar system. I'll come back on that when I'm talking about the specificity of the Earth and about life. Now, what I would like to explain a little bit further is we can do way more than just study the density, the mass, the size, and detect them. I think we can use feature of the transit specifics of geometry to study what is going on the surface of the planet. Surface in a general sense, it could be the surface of the planet literally, or it could be the atmosphere of the planet. To do that, there is two techniques. One of them is just to take a telescope, to look at the planetary system in transit, and to record the data. That's it, that comes, which is the light that comes in your telescopes. You get that, so essentially you have the time going on, and you see a drop at the transit, but you also kind of see mini drop, which is here secondary eclipse. We call that secondary eclipse. So that is the moment when actually the planet is behind the star. So the transit is when the planet goes in front, right? That remove a bit of the light from the star that produce this drop. But it's a moment when the planet is behind. You may ask yourself, why do we care? But actually, it's a very important moment because that's the only moment for sure you know you don't get any light from the planet. You know it's only from the star. So it gives you a kind of a reference point. So if you combine this on a kind of a zoom here, you realize that any light you get up to that point is the light of the star. Then anything above is a planet. This is how in 2007 the claim was made. We detected a light from a planet, and from that you can measure the temperature of the planet, especially if you work in the infrared, far infrared. So this is the kind of stuff we can do. So we can tell you, without almost seeing the planet, but just by the very detailed analysis of the light that comes, what is the temperature of that planet. And we're having a lot of surprise with the temperature planet, I can't tell you. I don't want to go to all of them, but there's so much diversity there. That's the trick we do. We can do way more, because we can come back to the transit and think about the moment when the planet crosses the disk of the star. So if you look at on the side, you have these three possibilities, essentially. Well, first, you have the light that hits the planet and don't reach your telescope, and there's a light that just doesn't touch your planet and goes through, that produces your transit. But imagine you have then high atmosphere and you have cloud. Any light that would hit this cloud would just stop as well. So essentially, if you take the planet and put cloud into the planet will look bigger. Because when you do a transit, you trap the global area that the planet is preventing the star to just reach your telescope. So if you put cloud, you expand a little bit the area of the planet, and then you make it bigger, and then you see it. So transit will be deeper at that moment. Now you can do even more, and we all know that when we look at the sunset, we all see that the sun turns red. But we all know that the sun doesn't change color. It just appears to turn red, because the red is the only light that crossed the atmosphere without being deflected. All the rest got deflected, or some of them absorbed. So depending on the color you observe, your transit, you will get a bigger or a smaller planet. And that is a super powerful technique, because that gives you access to the somewhat the X-ray compositions of the atmosphere of the planet, or something about the cloud. It's called transit spectroscopy, and there is a very intense view of that, especially with the wonderful machine we have now in space with the James Webb Space Telescope. But not only, it can be done also a big ground-based telescope to some extent. So to give you a bit of a flavor what we're talking about, I would like to steal one of this last result from one of my colleagues in Cambridge, Nico Madhusudan. This is the kind of data that is produced when you do these famous transit spectroscopies. What you have to think about it is on the horizontal axis is the color, the light that comes at different wavelengths that you measure at the time of the transit. And what you measure is the size of the planet at different light, at different wavelengths. And you see there are ups and downs, there are troughs and peaks, and it's a very confused measurements. But because we have a good understanding of how to solve the atmospheric situation, because it's temperature, pressures, law of physics, assuming some gas, you can try to solve and find out what is the best combination of the gas I can use to reproduce the data. And that gives you some kind of diagram like that, with the blue line being the theoretical predictions, the best matching the data point that you see through this data. And there's a lot of this data. What is fascinating with these measurements is that planet is what we call a mini-Neptune. So mini-Neptune is a temperate temperature, but that's kind of a very big planet. It's not a planet like the Earth. And the kind of molecule has been detected. Usually, they are not fitting together. You cannot have that kind of molecule. If you observe a Neptunes, you don't see that. So there is a long debate right now. How come you get these molecules? And one way to produce this molecule is to assume the planet has a solid core. So maybe we see here a kind of new kind of planet that nobody has thought before, with a solid surface on a big atmosphere, possible water, we still don't know about that open then the possibility that maybe there are other kind of planets that are rocky, that doesn't fit the kind of rocky planet telluric description that we have in the solar system. It's just a warning call here. Because of such a diversity we have to be very careful right now what we extrapolate on, and we should not be shy to try to explore maybe other configuration for planet with a solid surface. The reason why I insist on solid surface is because of the question of life, of course. So this is just the beginning of a long story, and the Webb is a wonderful instrument. We're just starting to use it, and I can tell you there is way more work and result that will come. Now, the fascinating element about all these many planets on short periods is most of them, they are just too hot. And that one is a kind of a short period system, so how come this planet could be moderate in temperature? Because here there's a trick. The star that this planet orbits is not a star like the sun. It's called the M stars. It's a smaller star because the star is smaller, the temperature is lower, and you can go closer to be still within a moderate temperature. You can imagine if you move the sun, you change the sun and you make it M stars, then the Mercury orbit will be a kind of mild orbit to sit in, because the light of the sun will be much less stronger, and then the temperature will be decreased on the planet. So we have a lot of this planet right now, and you have a very extreme case. I'm sure you heard about it. If you go to the very, very smallest stars, that turns out to be the more numerous in the galaxy, so it's cool, there are plenty. They don't shine very much, but there are a lot of them. We end up with a system like this system TRAPPIST here. Where essentially is a system of multi-planet that all rockies. They will all fit even smaller. You compare with the Mercury, you see all the system of the orbital system will fit into the solar system. So it's not even within the Mercury. It's within 10% of the orbit of Mercury here. You have the TRAPPIST system almost. But the star is different. It's much smaller. So when you compute the temperature regime, you can have a similar temperature regime that the solar system rescale. So it's kind of a mini-scale version of the solar system. And we have a lot of them. TRAPPIST is unique because it's a very nearby object. There's a lot of them. But the principle is there. So then it opens a complete new game. On one hand, you can study the atmosphere on some of the planet. And some of these planets in short period happen to have a temperate situation. So what about if there is water there? And then you start a complete new, different topic here. And to enter this topic, I have to move to a different level, and I have to come back to the baseline. And the baseline is this one. It's the Earth. Because wherever we have explored the solar system, we have not brought back many things except for the moon, which is a piece of the Earth, in a way. So that's the only planet we know so well, and we can study the planet, and we have this wonderful story about the story of the Earth, which is start here at 6 o'clock and goes around like a clock, and just to show you that the Earth was not exactly the same if you go back in time. In the very early stage, the Earth was very hot. They had a very heavy bombardment, which is great, because the bombardment came from the far side of the solar system, when there is a lot of carbon, CO2, essentially. There's a lot of this element. You have the cometary trail. All this is falling, so it's heavy in carbon. This is certainly why we have so much carbon on Earth. And then it cools down and produces atmosphere of CO2, SO2. And then something happened on Earth, which we call the prebiotic moment, when there's a turn and life pops up about 1 billion years after the beginning of the Earth. And then if you wait 2 more billion years-ish, a bit less, you have these great oxygenations, and then you change completely the atmosphere of the Earth. Now, this story is great because you understand that there's a link between all of that. But the story is a bit of a fake, in a sense, because the story for the first billion years, I have no data. It's just in my computer, essentially. Because we don't have any trace, except the zircons, what happened in the first billion years-ish. So it's only in extrapolations what can happen. And the reason why we have nothing is because we are alive, because we have the plate tectonics recycling the CO2, and recycling the CO2, recycling everything. It's a big washing machine. Any rocks on the surface will be dragged down, will be melted and reprocessed and came back as fresh as it could be when it's being back into the atmosphere. So we have this massive recycling. And that's the second idea here. I mentioned we can look at many planets, because we have an infinite number of planets. Nothing prevents us in astrophysics to look at planets that would be in some of this configuration that is like the Sun. We can even see some of them that are maintained in this situation. Think about a situation when you have a very hot planet like that, like a lava planet. We have system of lava planet because they're so close to the stars. So we can study these different phases that we believe were critical for the Earth by looking at many different planets. And we can explore and closer what happened in the prebiotic element. The second element, which is great, is if you try to translate this pattern that I explained into data, well, you can produce what the spectra would look like. And that is the production on the right, which is based on a study of a future space mission called LUVOR, to demonstrate that without having too many detail, you would be able to recognize a very different kind of phase into a planet compared to the Earth. And you see this is a spectra in this case that is being produced, the albedo, it's reflected spectra in that case. That is very different, depending if you are on the Archean Earth, which is before the prebiotic, Proterozoic is just before the explosion of the Cambrian, and then you have the modern Earth. So you have very, very different element there. Now, this is what we do in astrophysics. So you can start to extrapolate on all these systems. What does it mean, practically? And then I have to deviate a little bit and going a bit further down and starting maybe with, let's call what I call an aesthetic conjecture, which is not mine, which is the one of Christian de Duve, who, in a way, express a very simple concept that because we have life, I think there is something encrypted into the universe that can produce life. And in a way, for a physicist, not a surprise, we know that encrypted into the law of the atomic physics, you can make all the atoms in a star. You know that you can make stars. You know you can make planets. When you think about the beginning of the universe, there's not much. You just have a very simple baryonic matter, some leptonic neutrinos, and you have photons, not very much. But you produce in the star this massive amount of atoms that we all have in our body right now. And then on the planet, you produce the chemistry that complexify all these atoms into molecules and so on and so on. So this is really this concept that we have, that nothing should prevent us to solve it, because it's part of the law of physics, essentially, and life is part of it. It's a bit more complicated, but it took us a long time to find out how the sun would work and would produce all the nucleosynthetic process. So I think there is no reason why it cannot be done. But it is difficult. It's difficult, and so far we have to admit that we have not a single evidence of anything like life we have on Earth. This is just a fact. We only know one case, and anything has no evidence. Now, the good news is what Kell said in quotations, that the fact we have nothing doesn't mean that there is nothing as well. So that's why we are working hard, because we still believe that because we have no evidence of absence, we should find out. And that is the motivation for all the scientists working in this field. Now, we are bounded by two elements here. Very simple. The first one is simply the Earth. The life on Earth is a singular replica shaped by the evolutions. I will insist on that. There is only one life on Earth. I mean, you're not very different in terms of structure, in terms of foundation of the structure than trees outside. So that gives us an element of life, but that's a unique expression of life given the condition that happened on Earth. And I call that the singularity trap, because, of course, we have only that example. So we tend to lean on that example for good reason, because that's the one we have. So we have to be aware of that singularity trap and remind ourselves this is one boundary condition. So at least whatever we do, we have one which is here, we can study, and this is why people are trying to understand that bit. It's that element there. Now, it's a very complicated problem, especially the origin of life, because you have a very biased perspective because of the time and the evolution that have shaped life. One diagram we have to keep in mind is where you put the tree of the evolution of life through time. This is a lot scale here. You get this very simple perspective that the life we do see today, which is on the outskirts here on this diagram, which is today, and the more you get inside, and the more you go back in time, I think this immense diversity you have at the Cambrian explosion that we see, essentially what we see, I mean, obviously here, only came very late. It's 500 million years. But the whole process of ancestors, which are still there and dominating the game, they are the bacteria. That's really the one here. And if you look at us, we're just at the very end. You look at humans at the very down here. So it's very, very difficult then to work through that, because how do you use this immense diversity to tell you something that happened at the very beginning? That's one of these prowess that people are trying to fix, not by going backwards, but by going inwards, by trying to engineer life as close as possible to the way we see it today, with the idea that the evolution of life was crafted very quickly, and that's true, and then after there's a diversification of it, but the foundation of it, because everybody looks the same, essentially, they should come somewhere there at the beginning. It's called the origin of life study. So I'll give you one element there. The second boundary conditions, which is looking at the diversity of the planet. And then we have a very interesting situations. We have plenty of planets, so I hope you're convinced about this, and you hope you're convinced that a lot of them potentially life hosts, accounting for the fact that they are temperate. We're going to find water on some of them, is pretty clear by using these techniques I was mentioning. So there will be a lot of planets that we say, it's interesting. And there is still claims, and there will be, and there has been claims, and some of them are really potentially habitable, and so on and so on. So I think this is a fact that nobody will dispute. But then the problem is what I call something that, if you have played this game in the 70s, come from the 70s, it's the Conway's game of life. It's a computer program, a biologist invented that, and tried to simulate the evolutions of patterns, like species. And he came back with a very interesting conclusion, I think, in this game. Is many patterns you can do absolutely predictable. So you can put the pattern and you know it's going to happen. So they're going to merge in one direction, so they're going to oscillate and forever, and they're not going to change. But there's some of them that got out of control. And in general sense, you cannot predict what's going to happen. And I think that's a bit the problem we have. On some sense, there will be some cases that are clear-cut, because we say, yes, we understand that, we know what it means, but a lot of them, it will be not clear-cut, it will be not very easy, because it's so much incomplete, so you will have to run the game to really know what's going on. And run the game, it means you have to get obvious element to find out. And the obvious may not be obvious practically, because for a long time on Earth, there were no obvious traces of life when you look just the atmosphere of the Earth. So it's a bit the game we're going to play in the next 100 years, I think here, trying to be bounded between these two elements. One hand, to understand the life that came on Earth, which is good, with the possibility to extrapolate on what the possibility of having life on Mars has been discussed before, I think, and then Venus, and they have Enceladus mission, Europa, you have all these fascinating sites where we can go, dig, and come back, and it would happen. And then this immense number of planets we will have at the same time here. So due to the complexity of the problem, there is a kind of a mini revolution in a way we get structure in this field, because it's pretty clear, given the complexity of the problem, you cannot address it in a kind of a regular way. You have to team up beyond your usual expertise. So you have to work on problem that essentially you understand only 10%, and you will always understand 10% because it takes almost a lifetime to understand the complexity of the biochemistry, or maybe the complexity of to retrieve the data from a James Webb Space Telescope. So you have to talk together in a way to build up a common understanding how we're going to make sense into that. And I want to spend my last slide of this very interesting challenge, and it was mentioned that I started to develop a center. I'm not the only one, and those of you staying tomorrow will hear more, because Dimitar Saslov is in the audience. I was on the precursor and pioneer into this idea when you team up with different people and you try to work across discipline. And the reason why is a problem is a multi-element problem. It's a chemistry problem, it's a planetary science problem, it's also an astrophysical problem. And there is sub-problem you can fix along the way, specific to each of them. So you have to find your tiny bits of the problem. At the end, the prize is in the middle. But you don't need to reach the middle. And that's what I keep arguing. Asking me, oh, are you searching for alien life? I say, no. I try to understand what it means looking for life. How much do we understand the planet? How much is the consequence of life evolution on the planet before being able to answer the question, I'm going to find life? So it's a bit what is going on here, and what is very interesting also in terms of social education. So you are eating a lot of problems. I'm not talking about the internal problem of the structure of each of the academia that hate people that cross boundaries usually, because they cannot trace them on a matrix, on Excel sheets, so it's complicated. But just talking to each other, having the same language, a same world means something different. The famous joke in physics is the metal for astronomers. I mean, essentially anything which is not hydrogen and helium. So this is kind of stuff like that. So there's a lot of assumptions like that we do. And we have this limiting preconception element that we have to battle with. We have to remember whatever it is. And we have to, in a way, find a new way to work together. So it's a big adventure that I say we because there's a huge now momentum through the world. We are into it, and all this happens because 30 years ago we started to find planet, and clearly the discovery of the planet was a true evolution in that mindset, because now it leads to the development of questions which is understood and accepted by the community. Can we understand the origin of life on Earth, and is there life everywhere in the universe? Is it a universal process that creates life as the universe creates stars and everything like that? I will leave you with that. Thank you very much.